This entire video was done in one take, and now I'm going to reverse it. Cue the rewind. Now we would be reversing my one.
मैंने जिसे अभी अभी देखा है कौन है वो अनजानी वो है कोई कलिया कोई किरण या है कोई कहानी उसे जितना देखूं उतना सोचूं क्या उसे मैं कह दूं Pretty woman.
What's up, folks? This is Rev Bari, Ghana University Physics grad student. Today, I welcome you to the first episode of Graduate Classical Mechanics. So in this lecture series, we're going to talk about, of course, the Euler-Lagrange equations, Hamiltonian mechanics, but then we're going to move on to classical field theory, which is the prerequisite for quantum field theory in a sense. So we're going to see how field theory comes up with particles in a classical sense, and then that'll lead the way to quantum field theory. So today, let's hit the ground running with a problem that demonstrates the power of the Euler-Lagrange equation. And that problem is as follows. So consider the following. We have some kind of a coordinate system. Here's my x-axis, my y-axis. And what I have, the situation is that I have a bead on a wire. So here is my wire. Okay, it's going down. And I have a bead, some kind of a particle that's free to move on my wire, and the distance from the wire to the origin here is d. Okay, and this bead is free to move. Okay, so it's not necessarily on this shortest distance here. The bead can move up, it can move down, so on and so forth. So what's the caveat here? What do we have to figure out? Well, this wire is actually rotating around the x or y-axis, and its rotation is given by theta equals omega t, where theta is this angular displacement from the x-axis. So what the question is asking us is to figure out the equations of motion of this bead. Okay, that's what we have to do. Let me make sure the mic is miking. Okay, good. So to answer this question, the first thing we want to do is identify the generalized coordinates of the system. What do I mean by that? Well, the generalized coordinates of a system come from the Euler-Lagrange equations. So that says that dl dq minus d dt partial L partial q dot is equal to 0. Okay, now where does the Euler-Lagrange equation come from? Well, it comes from the definition of the action as the integral of the Lagrangian over time. Well, the Lagrangian is kinetic minus potential energy. And if we demand that the action of a classical system remain unchanged after a small perturbation, delta S, then we obtain the Euler-Lagrange equation. And in fact, I do that for a field theory in my QFT videos. So if you want to see the derivation for this, you can actually watch my QFT lectures on the Euler-Lagrange equation for a field instead of a particle. Now, in this case, let me put q sub I here to indicate that we might have multiple generalized coordinates. So what are generalized coordinates? Well, if you look at a pendulum, for example, not a single pendulum, but a double pendulum, something like this, then the generalized coordinates of this double pendulum are simply the two coordinates we use to identify which direction the pendulum is moving. So this is theta 1, this is theta 2. That means q sub I for a double pendulum would be theta 1 comma theta 2, and q sub I dot, aka the analog of velocities for a double pendulum, would be theta 1 dot comma theta 2 dot, right? Something like this. That's for a double pendulum. What about, let me give another example. If you have, for instance, a ball on a ramp or some box on a ramp, then the generalized coordinate is simply this vector, let's call it q, along the ramp. Okay, so here we have only one generalized coordinate, which is q, right? If you have, for example, light bouncing off a mirror, okay, so this is the problem I actually solved in my paper published in the Astronomical Journal. If I have light bouncing off a mirror, what are my generalized coordinates? Well, first thing you want to do, draw the normal line, and then the mirror is heading in this direction with the velocity v, and it's angled at some angle theta. And let's say a beam of light comes in over here exits over here, and the two angles of incidence and reflection are not necessarily equal. So this is optics. We're dealing with a photon, which is a massless particle, right? So here we won't necessarily have generalized coordinates, but if we did, then I know better than anyone that this problem has these generalized coordinates, alpha and beta. Or you can also think of it as follows. You can treat the photon as a billiard ball, in fact, and that billiard ball has a certain momentum, initial momentum pointing this way, p sub I, and a final momentum that's pointing this way. So you can consider those to be your momenta, and then from those momenta, you can apply the conservation of momenta and energy to derive the relativistic equation. So these are just a couple of examples to demonstrate what the meaning of generalized coordinates are. Okay, now that we know what it means, let's try to figure out what the generalized coordinate is for this system right here, where we have a bead on a rotating wire, and then we can calculate the equations of motion. Let me just make sure. Yes, okay, it's miking. So the generalized coordinate for this bead is going to be what? Well, let's say that this bead is not here. Let's say it's somewhere, just for pedagogical purposes. Let's say the bead has come down over here. Well, how can we characterize the location of this bead? Well, it turns out that the most efficient way to characterize the location of this bead is very much like an inclined plane. Just draw a vector that's along this rotating wire. Okay, let's call that vector Q. Okay, so now how do we classify the position and momenta of this vector right here, of this particle? Well, the first thing we need to do is consider what are the x and y coordinates of our particle here. So let me erase these other examples here, and let's think about what the x and y coordinates of Q are going to be. And then we can develop the Euler-Lagrange equations for this particle Q. So let's draw the picture once more over here. But now I know what my generalized coordinate is. I know that this minimum distance right here is d. Here's my particle with a mass m. And here's my generalized coordinate q. Okay, well, the first thing I'm going to do is say that the position of the particle from the origin, okay, this position right here, let's call that vector r. This position vector, I can think of it as the sum of this distance vector d, let's make it into a vector quantity, plus this generalized coordinate q. Okay, so in other words, the position vector is d plus my generalized coordinate q. Okay, so now what I have to do is decompose d and q into their x and y components and then sum them up. So let's do that. So first of all, for d, it's pretty trivial, right? This angle right here is theta. So my x component for d is going to be d cosine theta. My y component for d is going to be d sine theta. Pretty simple, right? Now what about for q? Q is going to be a little bit more complicated. So let's think about, that's where the real action is going to happen, figuring out the coordinates for q. So to figure out the coordinates for q, let's do this. First, once again, here's my minimum distance. Let's say my particle is here with mass m. And this is my vector q. Okay, it's along the wire right here. Here's the vector q. And I want to figure out what the x and y components of this vector q are. So what am I going to do? Well, it turns out this angle is theta, right? What if I make an auxiliary line right here that crosses through my particle, okay? And it also is parallel to this base of the x-axis here. So that means this angle is also theta. This angle right here is pi over 2 minus theta. And now we can probably figure out the components of q. Okay, what are the components of q going to be? Well, let's see. Let's draw this triangle over here again, and let's consider the scenario. We have theta here, a right angle here, and pi over 2 minus theta, and q over here. So we'd like to know the x and y components of q. So in other words, we'd like to know what this x component is and what this y component of q is. This is q sub x, this is q sub y. So how do we figure out q sub x and q sub y? Well, those are just the two different legs of this triangle, right? So let's try to figure that out. So this leg of the triangle is what? Let's call that, I'll just call it T. Okay, so we have this angle, okay, and we have this side. So opposite and adjacent. So we have tangent of theta is opposite over adjacent. So our side here is Q over tan theta. Okay, so that's our side over here, Q over tan theta. This is Q over tan theta. And what about our other sides? So this side over here is going to be what? Well, first let me label the side that we just got, this side over here. This is Q over tan theta. Okay, so that tells me what this length over here is. This is Q over tan theta. But I'd like to know this. I'd like to know this Q sub x here. So how are we going to figure out that Q sub x? Well, let's zoom in here one more time. Okay, let's draw the picture. Again, here's the diagram. Here's my shortest distance d. Here's my mass m. And here's my angle theta from the x-axis. And here is my parallel line cutting through m and also making an angle theta right here. And so now, and this is my generalized coordinate q. And so now what we just discovered is, okay, this angle right here is pi over 2 minus theta. So it's just 90 minus theta over here. Okay, now let's think about what's happening here. Okay, so the first thing we know is that this triangle here with a side length of d, okay, it has sides of d cosine theta and d sine theta. Okay, those are our two lengths here. And what we'd like to know is what is the x component of q from here to here and the y component of q. Okay, so the first step in doing that is just take a look at this triangle. Okay, notice that this is a right angle right here. And so I'm going to draw this triangle, reproduce this triangle right here. This is 90. So if this is pi over 2 minus theta, then this angle has to be theta once again. This angle is theta, and this is q. So to figure out q sub x, we simply need to use basic trigonometry here. So q sub x is what? Well, we have opposite and hypotenuse. So sine of theta is clearly opposite q sub x, our desired quantity, over the hypotenuse, telling us that the horizontal component of our generalized coordinate is q sine theta. So this q sub x is q sine theta. And likewise, let's do an analysis of the x component, of the y component. So this y component here is simply going to be sine of pi over 2 minus theta, right? So here, q sub y is equal to q sine of pi over 2 minus theta, but this is simply cosine of theta. And so q sub y is simply q cosine theta. So now we have all of our information. Just checking, the mic is miking, very good. So now that we have all of our information, we can now write down our position vector, r. So let's go ahead and write that over here. So r, remember, is our distance, d, plus q, our generalized coordinate. So what is d? Well, d is pretty straightforward. It's d cosine theta this way, d sine theta up. So d is going to be d cosine theta, comma, d sine theta. Now we're going to add to the vector d, the vector q. Now what are the components of vector q? You've got to be a bit careful because it's a vector, right? It's got to have direction as well as magnitude. So even though we have the magnitude, we've got to be careful with direction. Notice the y component is negative, right? X component is positive. So we're going to have q sine theta, comma, minus q cosine theta, minus q cosine theta. When I first did this problem, like 2 or 3 times, I made the mistake of making it plus q cosine theta. Of course, that's wrong because the y component is downwards, right? So now let's go ahead and add these up. So we have d cosine theta plus q sine theta. That's the total x coordinate of our particle. And d sine theta minus q cosine theta. Okay, very good. So now let me erase all of this. everything we don't need. Let's take this out. So now what we're going to do is figure out what our Lagrangian is. Okay, remember the Lagrangian is just kinetic minus potential, right? So the Lagrangian for any particle, any system, is kinetic minus potential. Why is it kinetic minus potential? Well, I wrote a whole paper on that, so I'll go ahead and read the paper Simulating Action Principle in Optics, published in the Physics Teacher, if you'd like to know the history behind that. But basically, if I wanted to give a 5-second explanation, Richard Feynman proposed an explanation for why the Lagrangian is t minus v instead of t plus v. That explanation comes from a competition of time. You see, if you run too fast, then time ticks slower because of time dilation. But if you're closer to a gravitational well, as opposed to being farther away, time also ticks slower. So if you're far away from the Earth, time ticks faster. If you run fast, time ticks slower. So you have a competition between something that wants to slow down time, going fast, something that wants to speed up time, going far from a gravitational well. So if you try to compete these two things against each other, then you emerge with the Lagrangian. Because look what you have in the Lagrangian. You have kinetic energy. That's the energy associated with speed, right? The faster you go, the slower time goes. And you have the potential energy. That's the energy associated with position. The farther you go, the faster time goes. So it turns out that the perfect balance, the perfect compromise between that minimizes the proper time for a particle is to subtract the potential energy from the kinetic energy. If you add the two, then you would get mechanical energy, but you would not get the Lagrangian, and you would not minimize the proper time for a particle that's trying to balance this competition between slowing down time due to going fast or speeding up time due to being far from a gravitational well. So that's a 30-second explanation of Feynman's argument, but go ahead, read my paper if you're more interested in the details. So anyway, the kinetic term is going to be 1/2 m x dot squared plus y dot squared. Now the question is, what is x dot squared and y dot squared? Well, we have x and y here. So x is, maybe I'll write it over here since the computation will be long. So x is equal to d cosine theta plus sine theta, d cosine theta plus q sine theta. And now we have to compute x dot, right? We have to take the derivative of this. So take the time derivative of x, and we get what? Well, this is minus d sine theta, theta dot, right? Because d doesn't change, d is just a constant. And here, we got to do the product rule because q can change, right? The bead can move up and down the wire, so q dot sine theta, and then plus q cosine theta, theta dot. Okay, now let's go ahead and derivative the y component. So the y component of our particle is d sine theta minus q cosine theta, d sine theta minus q cosine theta. Take the derivative over time, and you get what? Say, apply the same principle. This is d cosine theta, and then do the product rule. So minus q dot cosine theta, and then plus q sine theta, theta dot. Now we're going to square both of them and add them up. So that might look like it's going to be a bit of a pain, but that's fine. So first of all, I'm going to look at x dot, and I'm going to factor something that's common out. That's sine theta. So if I factor out sine theta, then what do I have in parentheses? I've got q dot minus d theta dot, okay, plus q theta dot cosine theta. Now likewise, let's do y dot. Y dot is, let's factor out a factor of cosine theta. And what do we have in parentheses? We've got minus q dot, so minus q dot plus d plus, now hang on, there's something off here because it should be symmetric. It should be d theta dot. So I took the derivative of sine theta, but clearly I forgot to insert a theta dot. Now, ladies and gentlemen, you can see here evidence that even a genius can make mistakes. So I clearly forgot a factor of theta dot right here. But thankfully, being a genius, I have corrected my mistake. So this is plus d theta dot, and then I have my regular plus q dot sine theta. Now we're going to go ahead and square both of these and add them up, and so that we can calculate our total kinetic energy for our particle. So let's erase all of this. and calculate x dot squared plus y dot squared to determine t, the potential, the kinetic energy that we'll need for our Lagrangian. So the first thing I'm going to do is square x dot. So let me move over here. So x dot squared is going to be what? I'm going to have sine theta. So let's see, sine theta factored out, and I have q dot minus d theta dot, okay, plus q theta dot cosine theta squared. Okay, that's x dot squared. And okay, let's do x dot squared first, and then we'll do y dot squared. Hopefully mic is still miking. Yes, very good. Because I forgot to charge it last night. So let's square this, the first term, just basic arithmetic. Q dot minus d theta squared plus q squared theta dot squared cosine squared theta, and then plus our factor of 2. So this being a large whiteboard, it can accommodate everything apparently. So sine theta, cosine theta, and then here I have q dot minus d theta dot. Very good. So that is all of that. That is x dot squared. And why don't we factor this out? I mean, spell this out. So this is going to be q dot squared minus 2q dot d theta plus d squared theta dot. Oh, no, d squared, just theta squared. Very easy to get your dots and undots mixed up here. Plus, let's see, q squared theta dot squared cosine squared theta, and 2 sine theta cosine theta is just sine 2 theta, q theta dot, q dot minus d theta dot. Very good. So this is x dot squared. Now we're going to do y dot squared. So y dot squared. So now we're going to square all of this. So I'm going to have the parentheses cosine theta minus q dot. Okay, all right, something's going on. Minus q dot plus d theta dot. Okay, plus q theta dot sine of theta. All right, so now immediately before I even do any math, notice that this right here is the same as this, right? It just except for minus sign. So let's go ahead and calculate this. So I'm going to have cosine squared theta. And then here, I'm actually going to have the same term, right? Because this is just minus of this, right? This is q dot minus d theta dot. This is just negative of this. So I'm going to write the same thing, in fact. Q dot minus d theta squared. Okay, work smart, don't work hard. So now I'm going to have, let's see, q squared, I mean, theta dot squared, sine squared theta. And then my factor of 2q, well, what do I have here? 2q theta dot sine theta, cosine theta. And then I have my minus q dot plus d theta dot. Okay, very good. So that is our entire y dot squared. And now let's go ahead and see if things simplify when we add these two things up. So x dot squared plus y dot squared. Let's see. Well, first thing I recognize is that I have sine squared theta times this q dot minus d theta squared, cosine squared theta of the same thing. So when I add up, so when I have x dot squared plus y dot squared, then I'm just going to be left over with this inner term, right? Because when I factor it out, sine squared theta, cosine squared theta are going to equal 1. So I'm going to have q dot minus d theta all squared. Okay, moving on. So I have q squared theta dot squared cosine squared theta, same term with sine squared theta. So once more, this is going to simplify to just q squared and theta dot squared. And now let's take a look at our last term here. All right, so something crooked is happening here. And what is that crooked thing? Well, notice that these two things are just inverses of each other. They're going to cancel out, thankfully. So this is just going to simplify to what? Let's see. So I have q dot squared minus, actually plus d squared theta squared, and then minus 2q dot d theta plus q squared theta dot squared. All right, ladies and gentlemen, and that is the kinetic energy term for our Lagrangian for this particle. Okay, let me write it over here. Okay, so, and what about the potential energy actually? Maybe we can quickly do the potential energy as well since we're so close. The potential energy is just mgy, right? It doesn't get easier than that. So this is mgy, where y is the y coordinate. So what's the y coordinate? That's just d sine theta minus cosine theta, right? So in fact, I can write my entire Lagrangian right now. Okay, hopefully the viewer's sanity has not been lost yet. So the total Lagrangian for this particle is going to be the kinetic minus the potential. Remember, this is our kinetic term. This is our potential term, right? So our kinetic term is q dot squared. Q dot squared. May the Lord Almighty help us write this Lagrangian. Minus 2 q dot d theta plus q squared theta dot squared minus, and now I have d sine theta plus q cosine theta. It doesn't seem like anything cancels out when I wrote my entire Lagrangian, but that is it. Okay, and now that we have our final Lagrangian for this particle, we can use the Euler-Lagrange equation, right? Remember, the Euler-Lagrange equation says the derivative of the Lagrangian with respect to one of the generalized coordinates minus the time derivative of the conjugate momenta, partial L partial q sub I dot, is 0. So the only step we have remaining is to apply the Euler-Lagrange equation to this Lagrangian to figure out the equations of motion. So folks, that's it for this video. This entire video was done in one take, and now I'm going to reverse it. Cue the rewind.